Today we're going to be talking about solving trig equations. It's the first of two videos on this topic and is video 5.3a in our sequence. You may notice that the sequence has been renumbered to match with the numbers of the sections in your textbook and for the problem sets. Hopefully that will reduce some confusion. Our goal today is to use our understanding of identities and our knowledge of algebra to solve some equations involving one or more trig functions. We've done this before. In our last chapter we looked at solving some trig equations that involved one function and using the inverse to undo the trig function and get a solution. Today we're going to be looking at some problems that are a little bit more complex. Some of the general ideas here are to use what you know about algebra, things like collecting like terms on the same side of an equation, doing some factoring, especially for quadratic or polynomials involving trig functions of a higher degree, and using your trig identities to simplify an equation down to a single trig function. The overall goal here is to isolate, in other words, get by itself, a trig expression and then solve. In our first example, we're working with the equation 2 sine of x minus 1 equals 0. The first thing I'm going to do is isolate this trigonometric expression. Get my sine of x by itself. To do that, I'm going to add 1 to both sides and then divide by 2 to get sine of x equals 1/2. The second thing that I'm going to do is use my inverse sine, arc sine, remembering that the arc sine of sine of x is equal to x. The inverse of a function taken in composition with the function itself will produce whatever's on the inside of that function. So if I have sine of x equals 1/2, what I'm going to get is the arc sine of 1/2, and that's going to produce an angle. It's actually, if we look at our unit circle, going to produce two angles where the coordinates of the central angle will have a y-coordinate equal to 1/2. An angle in the first quadrant and an angle in the second quadrant. The angle in the first quadrant is going to be pi over 6, also known as 30 degrees. The angle in the second quadrant is going to be 5 pi over 6, also known as 150 degrees. So between 0 and 2 pi, this can be written in a couple different ways, as words, as an expression using inequalities, and an interval notation, remembering that a squared off bracket means inclusive, so 0 is included in this, and a curved bracket parentheses is exclusive, means that 2 pi is not included in this interval. So between 0 and 2 pi, we have two values that fulfill this equation. Those values are pi over 6 and 5 pi over 6. With trigonometric functions, we have a problem of solutions. If I take a look at the end product of the equation that we just simplified, sine of x equals 1/2, really this provides more than just two solutions, pi over 6 and 5 pi over 6. It provides this angle, pi over 6, and every coterminal angle that's going around and around and around. Every 2 pi we have one more angle that's at the same place. So not just pi over 6, but 13 pi over 6 and 25 pi over 6. That should be a 6, I don't know why it's a 2. 37 pi over 6, adding 2 pi, 12 pi over 6 each time. The same is true for our 5 pi over 6. Not only is 5 pi over 6 a solution, but also 17 pi over 6, 39 pi over 6, 51 pi over 6, and so forth. The problem is that we have lots of solutions. In fact, we have an infinite number of solutions to any trigonometric function that doesn't give us an interval to look inside. We have a shorthand to help us simplify these matters instead of having to write an infinite number of solutions, which would keep you busy until, well, longer than any of us will be alive. We use this notation. Here I have pi over 6 plus 2 times n times pi. What this is saying, and we're going to use n for integers, is that every time you go around the circle once more, you're coming up with another coterminal angle, another solution that would work for this. Since the period of sine is going to be 2 pi, we use 2 pi times n for our integers. So if n is 1, we go around one extra time, 2 pi. If n is 2, we go around twice more, that's 4 pi. If n is 3, 6 pi, 3 full circles more, and so forth. The same is going to be true of 5 pi over 6 plus 2n pi. In a second example, we have a problem that's a little bit more complex because we have a sine function on both sides of the equation and a number that we have to deal with. Let's collect both of our sines on the same side and give us 2 sine x plus the square root of 2 equals 0. Isolating, once again, this sine of x, we subtract square root of 2 from both sides, and I'm left with 2 sine of x equals the negative square root of 2. When I divide by 2, I have sine of x equals the negative square root of 2 over 2, which should seem like a familiar ratio for you to get because we know it's a special right triangle associated with 45, 45, 90 right triangles. If I take the arc sine of both sides, I get 2 angles between 0 and 2 pi. There's the interval that I'm looking for. I get 2 angles that are true, 5 pi over 4 and 7 pi over 4. If we think about our unit circle, we're talking about the angle 5 pi over 4 and 7 pi over 4, where the y coordinates are both negative. For our third example, we go a little bit further with our complexity. We're looking for 3 tan squared of x minus 1 equals 0 for the interval from 0 to pi. Alright, if I'm looking for a way to isolate tangent of x, let's start by adding 1 to both sides and dividing by 3. Then I'm left with tan squared of x equals 1/3. To get rid of that tan squared, first I'm going to take the square root of both sides. The square root of tangent squared is just the tangent of x. The square root of 1/3 is plus or minus 1 over the square root of 3. If I rationalize that denominator, it's equal to plus or minus the square root of 3 over 3. Depending on how you organize your trig table, you may have solutions that look like either one of these, and that's okay. If you're using a calculator, either one of these being typed in will give you the correct answer. If we take the arctangent of both sides, we come up with a solution for the positive and a solution for the negative. We have pi over 6 equals x for the positive, square root of 3 over 3, and 5 pi over 6 equals x for the negative square root of 3 over 3. For our last example, let's look at a problem that's more complex still. This time we have both cotangent and cosine being used in the equation. Let's take a look. At first I have cotangent of x times the cosine squared of x equals 2 times the cotangent of x. First, let's collect our terms to one side of the equation. by subtracting 2 times the cotangent of x from both sides. Then I've got cotangent of x times the cosine of x squared minus 2 times the cotangent of x equals 0. Next, let's factor out a cotangent of x. I can see that this is part of both of these terms, and if I factor this out, it gives me something that's a little bit more desirable for us to work with. I have cotangent of x times the quantity of cosine squared of x minus 2. This is nice because we have two things being multiplied by each other that have a product of 0. This is going to give us two sets of solutions. The first is going to be based on if the first part is 0. The second is going to be based on if the second term is 0. I hope you remember doing this when you're looking at quadratics and you're looking at polynomial functions. We're going to use the same strategies when we're talking about trigonometric functions. Let's handle the cotangent of x equals 0 first. If I do arc cotangent of x, if I do arc cotangent to both sides, that's going to cancel out our cotangent function, leaving us with x. The arc cotangent of 0 is going to be pi over 2. Alright? Since cotangent has a period of pi, remember that cotangent and tangent have a period of pi, while cosine, sine, cosecant, and secant all have a period of 2 pi. Since cotangent has a period of pi, we're going to drop the 2 to get the general solution and get pi over 2 plus n times pi. But we're not done. We still have the second term, cosine squared of x minus 2 equals 0 to solve for. Let's isolate my cosine squared of x by adding 2 to both sides. Cosine squared of x equals 2. If I square root both sides, I'm left with the cosine of x equals the square root of 2. The square root of 2 is about equal to 1.4. We know that cosine as a function has a range between -1 and +1. 1.4 is out of that range, which means that we're not going to get a solution for this. So the only valid solution we have for our general solution is x equals pi over 2 plus n times pi.